on. All right, so computational thinking. I think we've used this term before. Oh, look, I lost my glasses are broken. I only got one. So that's not good. More people coming. Welcome. I don't like it when that happens. Got another glass here. Yeah, that'll do. So computational thinking, we actually have a term for that. There was this lady named Jeanette Wing, I think. She actually standardized the meaning of computational thinking. Not just her, a lot of other people were talking about it. But I think around 1995 through to 2005, there was a lot of discussion about that. So you can look at that. I will give you a paper by Jennifer Wing sometime. But if you Googled her or went onto YouTube, Jeanette, I think, computational thinking and Wing, you'll find articles by her. You'll find YouTube videos where she talks about computational thinking. So I encourage you to go and sort of find out about, I think her name is Jeanette or Jennifer. She sort of talks about what is computational thinking in a way which is now standardized. And here's it kind of. This is sort of what she's saying, what other people are saying is computational thinking. So we're using it to solve problems. That's a good, because this course is about solving problems, right? So it's using it to solve problems. Now, some of those problems we could use in the solution of those problems. So computational thinking can relate to that, but not necessarily. You could use computational thinking to solve other problems which do not involve using a computer in the actual solution of it. But we often use it in a way that we could use a computer to help us solve that problem. No notes on that. Now, as I said, computational thinking is an idea which has been standardized. And so we have this nice little graphic here, which has split out 4 different components of computational thinking, or 4 things upon which computational thinking is based. Or you could say, if we were to divide computational thinking into more than one way of thinking about it, we've got 4 ways of thinking about it here, or 4 things that we can do, which are computational thinking. Today, we're going to talk about it generally, and then later in lesson 6, which is next lesson after this, we'll look at pattern recognition, which is that one down there. But we've got 3 other things: decomposition, breaking things down into smaller components. You have a very big problem, which is complex. That means it's going to be hard to solve it because it's hard to understand it. You can't solve a problem until you understand what the problem is properly. And so breaking the problem down into smaller components that are more easy to understand, that's represented by this graphic here. If you notice there, we've got a big circle with the, which then is being split out into smaller circles. Eventually we get something small enough that we can approach that and solve that on its own. Then we can go backwards. So that's decomposition. Abstraction, kind of similar kind of idea, I guess you could say, where we take something which is complex and we remove from a representation. So we build models. We remove from a representation of some system everything which is not exactly what we have to work on for our solution. We do this in mathematics all the time. So in mathematics, we have abstraction to equations. You know, you'll have a story like, you know, I'm driving my car down the road at 60 kilometers an hour, you know, and I'm going to get to Doha which is 280 kilometers from where I am. How long is it going to take me? Well, you can abstract that, right? You could just say, okay, well, the distance is 280, the speed is 60 per hour. You know, from that, I can take the 280 and divide that by 60 and get a time. All the other stuff about my car and Doha, you know, is not, you know, I can abstract that away. I can remove that. All I need is the equation, which says that the distance, d, is equal to the time, t, is equal to the distance divided by the speed. You know, so you could do that, right? That would be an abstraction. We'll see more about abstractions later. Algorithms, we'll talk about that later too, which is basically a step-by-step way of solving problems. And today, as I said, later we'll talk about pattern recognition. So hopefully that sort of explains that. So a little bit more on each of those problems often that we receive, and problems are not just things that you have to do and solve with a computer. You could have a problem where, you know, your car won't start, right? That's a problem. How do we solve that problem? You might have a method of doing it. If you talk to a mechanic, they might have a better method. But for sure, you would try and isolate that. When I say isolate, I mean separate from everything else, things that could be the cause. You know, is there a problem with the electrical? Is there a problem with the gas? You know, these type of things. You would break it down into smaller problems. That's our decomposition. Pattern recognition is where we notice that we see something is happening more than once, happening over and over again. That's a pattern. Some component of it is happening. If we find something like that, we can generally make a little module that will just solve that in the general case and then apply it over and over again. Abstraction, as I said, is remove everything which is not important. Then we get to the idea of algorithms. Algorithms is going to be some model solution, which is going to be step by step. We can represent an algorithm using a flowchart. We talked about that last time, right? So an algorithm can be represented with a diagram. Flowchart is a diagram, or it can be represented by a lot of words. For example, pseudocode. And then we can take that algorithm and we can code it into a program. How are we going, folks? Is this making sense as I'm speaking to you? I hope it is. All right, so just let me know if it's sort of just sounds too weird. So I think we talked about that, right? So as it says here, we have to interact with the computer to solve problems sometimes. So how do we get that from that point? From the point where we're looking at a problem which is a human understanding, to get it to a situation where we can put something into a computer and let the computer help us to solve the problem. Well, that's going to take all of those things that we discussed there, that we're trying to discuss, which is our decomposition, breaking it into smaller points, abstracting, removing all the things that we're not going to put into the computer. What were the other ones there? Let me just refresh my memory on that. Abstraction, pattern recognition. If we see something which is repeating, that we'll focus on that for a module, and then our algorithm. So we will try and sort of do that. We'll not just we'll try and do that. We'll absolutely have to do that if we're going to take a problem and solve it with a computer. We're going to have to use these processes. All right, so we have an example. So supposing that you are going to meet your friends at some location, maybe it's in the city or whatever, for whatever reason, you know, just maybe it's just a social thing, and you have to decide how you're going to get there. There'll be some planning involved, which will involve some of your knowledge about the streets. You know, what streets am I going to use to get there? Maybe about the timing, you know, is it busy? That type of thing. And so from that, you'll have some step-by-step. You could put that into a computer program, and then you could run that computer program on your phone. For example, every time you use Google Maps or Waze or something like that, that is somebody has written a program. Actually, a lot of programs. That's actually quite a complex thing, and we know, and a lot of very smart programmers are working on that. There's a lot of things that have to happen to make Waze or Google Maps work. But if we remove from that just the simple thing of I need to go from here to there, I think that you could imagine a bunch of steps that would look kind of like the steps that you'd see coming out of Google Maps to get you from one place to another. I hope that makes sense. So we have a task, and this is new. This wasn't in there when I gave the lesson this morning. So let's have a look at that, right? Isn't that the same thing? All right. So yeah, this is just this problem that we've got here, and they have broken it down. So, all right. So you need to consider time, money, weather, friends' interests. Yeah. So, I mean, what's the fastest way to get from here to, I don't know, Dukan or Old Airport or something like that? What's the fastest way to get there? That might change depending on the time of day, depending on the traffic. Your money. Okay. So if you have a car, you know, maybe if you don't have a car, then you'll have to look at other ways, right? Yeah. Are you going to ride in the metro? Or are you going to catch a bus? Or are you going to use Uber? And all of those, there will be a different weather depending on that. Sorry, there'll be a different money depending on that. Now the weather, if it's like 50 degrees, you don't want to be standing around outside too much, right? You probably want to just get in your car and go. That would be the way you'd probably do it. I think that that's what it's getting at here. Do you think that you and your friends could decide more easily where to go in order to, from this information? Yeah. So the idea here is before we make any decisions, before we make any plans, we probably want to gather as much data about that as we want, because any one of these things could affect the way those decisions go. Hope that makes sense. Okay, so possible things to consider. Where could you go? Who wants to do what? Yeah, all right. All right, some ideas. Let's look at our notes at the bottom here. Oh, that's basically all there. All right, so any decision, a lot of inputs. That's all I'm going to say about that. I think that's enough. All right, well, here's something that looks like a game. Look at the video game screen to the right. What do you need to consider in order to complete the level as efficiently as possible? I guess this is you as a gamer. These things are enemies, and these are items that you need to collect. I guess if you collect that key, that might help you to, I don't know, maybe get over those things or climb up the ladder or whatever. So you want to get here. What do you need to consider? I would try and avoid them, or perhaps you have some way of disabling them, which you will do that. It looks like you have to find a path up there. It looks like you can't just go through the bricks. So you probably have to go around there and go past them somehow. Yeah. Yeah. Anyway, so what items do you need to collect? Looks like there might be something like that. How long you have? Yeah, there's a timing, right? So these things move around. They have a speed. Where's the exit? Where's the exit? I don't see an exit. Yeah. What kind of enemies? Yeah, maybe there's something about the enemies that you can disable them. As I said, maybe they have some weakness. Now you guys have better games than that, I'm sure. I mean, my daughter could tell a lot about what to do there. Is there anything more that we need to say about that, about the computer games? I think that's probably enough. Well, let's look at this. Right. So thinking computationally, here's another task. Can you put in the correct statements below? Can you put the correct statements below in a table? All right. So they have been color coded for you. So in other words, the yellow is going to go in here, I suppose. I guess the green's going to go in there. Yeah. But I think what they want them to do. So not all of these are correct. Some are and some aren't, I guess. Okay, so complete the level. Creating a computer game. Would you want to include explanation on how to complete a level? Can I move that? Kind of. Yeah, I can move it. So would that go there? Explanation on how to complete a level? Agree or no? I think that there should be some notes given to the user. Or you just want them to find out by themselves? Okay. So, I mean, that would be the choice that you'd make, right? Either they find out by themselves, or you tell them, right? Ways of getting to the exit, same idea, right? So it depends on what is your, how much help you want to get the user. For me, location of the exit, or they're just going to find that out. So, I mean, with each of those, used within similar games, I think for me, if from the point of view of the user, I would want all that stuff. I might not want all my competitors to have all that stuff, but I would want all that stuff. All right, so meeting up friends. Yeah, I think we decided that if you're going to meet with friends, it's not like a computer game. You do need to know where you're going to go. You do need to know some ideas on what transport you could use. Can I get it in that space? It's kind of hard. Oh, yes. Where you're going to go, that would probably be a good idea. I mean, actually, this color coding just makes this too easy. What you have previously, you get the idea, right? So they're all there. Explanation of how to, we talked about that. Focusing on important information only, that's called abstraction. So this one here would go there if it will fit. Yeah, that's abstraction, developing step by step. What's that called? That's called who? That's developing an algorithm if we're going step by step. Now, does that fit on top or underneath? Fits underneath. Looking for similarities among problems. Pattern recognition, got it. So that one going to go there. Breaking down a complex problem. That's decomposition. So that's nice. We got those there. So decomposition, breaking it down. Pattern recognition, looking for, yeah, okay, one thing hides behind the other. I think for me, I do like to help people with their game. So, and I would like to be helped. So, I mean, I would actually put these in there, but you know, you don't have to. Isn't that fun? Sort of. Or maybe you just want them to find that out on their own. Anyway, so we did that. Yeah, that's how they did it. They would do that too. That's what we just did. So I don't need to spend time on that. Decomposition, let's talk about that for a bit. All kinds of problems, personal, marriage, car, etc. Are complex problems that can be broken down into something smaller. We imagine, as we imagine. Now we like to have problems, right? You're all going to say no. Why? Because problems add to our stress. Stress is always bad, right? There's no such thing as good stress. Actually, I think there is a good thing about stress. So, I mean, like yesterday, I went in the desert. I spent the whole day in the desert from like 9 o'clock until 9 o'clock. It was hard. I fell off a few times. One point I thought I was going to break an arm. I didn't. I was worried about running out of time. And there was a lot of problems that I faced with my motorcycle. Will I do it again next week? Absolutely. Because I like those problems. It's fun. Problems are fun, no? Because especially when you solve the problem, then it's really, really fun. It's like, okay, so, you know, we had this problem, that motorbike didn't go there, and I did this, and now it does. I think we like to have a challenge. I'm a pretty old guy, and so for me especially, I like to have it because, you know, otherwise what, I'm just going to go and sleep on the couch or something. You know, I mean, it's actually something that keeps us alive. You know what I mean? So I think we like to have problems. We like to solve problems. When we solve problems, we feel like more powerful. It's nice to be powerful, I think, don't you think? So, I mean, this is what you're entering into in your career is to become more powerful, to solve problems, which is a good thing for you. And it's a good thing for everybody else, all the problems that you're going to solve. So we had a problem here in Qatar a couple of years ago, and we still have this problem, which is there was this disease that came, right? And so what do we do about that? Well, so what was the problem? The problem is, you know, that actually some people died. That's obviously a big problem. And so we don't like that to happen. And some people died, and then a lot of people actually had to go to the hospital and they had problems in their lungs. And so that's the big problem. So that's the problem that we want to kind of solve. And so some IT people sort of came up with a solution, which is, well, after the doctors looked at it, and said, well, you know, it'd be really good because this disease is contagious. It'd be good if people stayed away from each other a bit. And it would be good if we knew who had the disease and who didn't. So what we can do is maybe we can use people's mobile phones because everybody's got one. And we can put something on there, a program which will record what is their status in terms of with reference to the disease. And so if they have the disease, we can keep them away from everybody else. And so if they have the disease, they'll get a red thing. And so they have to stay home. And other people won't be in contact with them. That'd be a good thing, right? And so, yeah, so that was a problem and there was a solution. Now, it wasn't an easy solution. It wasn't something that, you know, just some guy, you know, down at whoever's doing the IT for the government just sort of came up with the idea and is on a weekend. It's quite a lot of computing went into that, right? And there would have been many people involved in sort of developing that application so that we could have that. We all have it now, and it's helping to solve the problem. It hasn't stopped the disease, but it helped to solve the problem that the hospitals have of too many people coming at the same time, right? You know, too many people with that could be really bad. So if we can keep people out of the hospital because they're healthy, then the people that really are sick can go to the hospital and get better. And so, yeah, so INFS is pretty good in that way. So that's a problem, complex problem. That's where we need the decomposition thing, right? That was a complex problem. We got this disease, it's very complex. How do we keep people away from each other? That's a complex problem. There are a lot of components into making INFS. And so where do you start? And we have to start step by step. Well, there's an old saying, right? Even the journey of 1,000 miles starts with a single step. I don't know if you ever heard something like that. That's the idea, right? Yeah, we have to see what is the next step, and then we just have to take it, right? And then eventually we will get there. It might seem like something big, and that's certainly the way it is with computers as well. As we have to do things. You'll have projects that you'll have to do, which will fit to this quite well, where it seems like there's a huge amount of work. And what you really have to do is you have to analyze it, see what it is, so you can break out something simple that is something that you can do now, and then do it. Rather than just sort of trying to attack the thing. Now, I'm going to kind of contradict that in a second, right? The key word there was analyze and decompose. We don't want to start off with a big project, which is a computer project, by going and starting writing a bunch of code, you know, going and making a big thing. What we need to do is the first steps is really about understanding the problem. And so that's where we decompose the big problem into a smaller one until we can understand it. We shouldn't be actually doing any building until we've really understood what the problem is. Otherwise, we get some big troubles. Okay, so I think I'm just going to go on there. Now, the point here is about the fact that computing is not just completely science. There are degrees that are called computer science degrees, but there are also degrees that are just more applicable degrees. You know, computing program degrees are not always called computer science. So actually, the degrees that we're offering here are not computer science. They're computer application science or applied computer science. So the word applied is in there. So the idea behind the applied thing there is using your creativity. We all have some creativity, right? Creativity, I guess you could say that's the artist side of us if you want, but some uniqueness that we're going to bring to it, something which is just out of our minds alone. That would be our artist side of things. And that definitely is important in computing as well as in other things, right? So there is something that you can offer, which is creative. So your way of solving a problem. Now, we use some standardized tools. So there's some things that we're going to do in the same way. But, you know, also a lot of computing, we have user interfaces. And so user interfaces have colors, they have graphics in them, and that's going to be very sort of artistic side for you as well. Not everything can be systemized, as it says. However, we do have a systematic approach that's possible for us. It's this fellow by the name of Polya who wrote this idea here. I hope if you notice what's on the left and what's on the right, there's sort of a similarity between them. I don't know if any of you studied science at school. If you did, you might be familiar with what we call a scientific method. And scientific method, form a hypothesis, plan experiment or experiments, execute the experiments and evaluate the results. That's a scientific method. The idea of a hypothesis is something which can be proven or disproven. And actually, in good science, we try and disprove a hypothesis. So we'll say, I think that this is going to happen. Now I'm going to try and prove that it's not going to happen. And if I can't prove that it's not going to happen, then I'm satisfied that that might be true. Does that make sense? So that's what we'll try and do. And in science, it's always going to be open, because I'll then write my paper and say, I think this is what was supposed to happen. I tried to prove that it was not, and I wasn't able to. So I think it's good. And then other people will read your paper. And they'll say, well, okay, we'll try and prove that it's not true. And if we can't prove that it's not true, then that goes up a little bit higher in value as being something that could be true. And you know, over years and years, nobody's able to prove that it's not true. We start accepting that it might be true. Does that make sense? But there's always a chance that it isn't, right? Because some smart scientist could come up with a better experiment that is able to show that it's not true. And that's always open. So we form a hypothesis. Well, I think this is true. I try to prove it's not true. I wasn't able to prove it's not true with the experiments that I have. So I'm going to say that, there you go, rest of the world, scientists out there, you try and prove it's not true. Otherwise, we're going to say that this is what we think is happening. Okay? Now, how about with computing? It's not quite that scientific, right? But, you know, we got something that sort of relates to it. Instead of forming a hypothesis, we try and understand a problem. Forming a hypothesis is where we're trying to imagine, we think that this is something out there that's true. Here, we think that this is what the problem is. I think I understand the problem, right? Then I'm going to devise a plan how I'm going to solve the problem. That's kind of like making experiments, kind of like. Then I'm going to go and do that thing. And then afterwards, I'm going to review it. So I think that was a nice application of something that's been working pretty well for a long time. Now, when I say it's been working pretty well for a long time, philosopher, scientist, whatever you want to call him, Aristotle, I mean, we're talking 2,000 years ago. He basically came up with this kind of idea, right? So, I mean, it's been around for a long time. It's worked pretty good. And so we're still using it, and it does have some application to computing, I suppose. All right, it might seem that when we try and come up with we have a problem in front of us, it might seem that that problem is overwhelming. And yeah, so when it's overwhelming, we want even more so to try and sort of break it down into smaller things. Notice here the point about resist the urge to jump in and start writing code is what I should say there, right? We don't want to just start writing code because at the start, you won't fully understand the problem. And so you won't have the best idea on how to make a solution. So that's the thing about defining the problem. Defining the problem is like to say, the situation now is not how I want it to be. How I want it to be is the goal. When I reach the goal, this is what I think it will look like. So we need to have that in our mind. What will it look like when I'm there? If I don't know what it's going to look like when I'm there, I haven't done my understanding of the problem well enough yet. So you have to get to that. We have to know what it is that we want it to look like in the end. So in this slide, it talks about desirable state and undesirable state. These are the things that motivate us as humans anyways, right? I mean, you wake up in the morning, you have you have an undesirable state, which is I'm a 20-year-old that doesn't have a degree. That's an undesirable state. And so I want to go to a desirable state, which is I want to be a 23-year-old with a degree and a nice job. So that's my nice thing. Yes. I was older than that. First degree, I was 22. Chemistry. Yeah, it was a long time ago, right? They didn't have IT degrees back then, or well, not at the university I went to. So yeah, so that when I was 20, yeah, that was an undesirable state, right? My desirable state was I wanted to have a degree and have a job. And I guess it's the same for you, right? That's your desirable state. And so you have identified that, and then you made yourself a plan. I'm going to get to my desirable state. Well, what I'm going to do is I'm going to enroll at the College of North Atlantic because I have a degree that I'd like to do. And now I have to break that down. Okay, this year I'm going to do this. And we help you a lot with that, right? We got people with registration office that help you, got people up there that help you. But you had to go through and do a little bit of planning. But you had to understand why it's undesirable. Well, why do you need to get a degree? Why would you do that? You can just sit at home, watch Netflix. But somehow that's undesirable state, right? Your desirable state is to have a nice job, have a nice office. People respect what you do. You respect what you do. You're able to make a contribution to your family. All those things, I imagine. And so you have that desirable state. That's the goal. You know what it looks like. You know what it looks like. It looks like I'm walking across the stage, collecting my degree, and then I'm going to my job. You know what that looks like, right? So that's your desired state, and then you can go ahead and sort of work towards it. Now, so other problems on the way, you're going to have a project that you have to do. You're going to have an assignment that you have to do. Your desired state is getting an A+ for that assignment, right? And so you understand that. then you have to understand, well, what do I have to do to do that, right? And then you'll work towards that. Sometimes it seems slow. I'm sorry, I'm going to run out of time on this. It's taking, all right. So Paulia says that we need to understand the problem. We can use diagrams to represent that. Do you remember in our lecture last week, we talked about flowcharts. Flowcharts is a diagram which is going to represent actually a solution to a problem, but we can use it for understanding the problem as well. Right. The purple stuff, I suppose, is important. So let's look at that. Whatever the problem, the key thing to remember is the goal defines the needs to be done and how, and not how it should be done. So that comes into the creativity thing as well, right? When you write a computer program to solve a little problem, as a teacher, when I look at people's computer programs, I shouldn't see two people did the same program to solve the same problem. I mean, we have trivial programs that we're going to start with, you know, writing a program to make an average or something like that. Yeah, the code's going to be basically the same, but different people should use different variable names. You know what I mean? They're going to have, there's going to be some slight individuality in everything. So I'm just saying that that's what I notice as a teacher. I'm going to see that. Yeah, everybody's going to do things in a slightly different way. They're not all going to start with from the point of knowing exactly how they're going to do the solution. There's going to be some creativity that's going to sort of come in there. Oh, I'm running out of time. That's my frustration. I'm sorry. This one does take a little bit of time. I mean, the idea here is you're going to have a conference, and your conference is like 3 months from now, and it's a pretty big conference. You're going to have smart people come, and they're going to talk, and so it's a type of thing that would require a bit of organization. So the idea here is, what are the things that you would organize first? Where would you start? So would you start with organizing the snacks, or would you start with deciding what is the topic of the conference? I hope it's obvious to you that you wouldn't start with organizing the snacks. I mean, organizing the snacks you could do the day before, right? You know, or the week before. You know, you call up a caterer, because you and actually you don't want to start with organizing the snacks at the start, because you don't know how many people are coming. You don't know who those people are and maybe what kind of snacks they like. So that's the type of thing that you'd want to kind of do later once you've got that kind of information. On the other hand, you probably would want to start with knowing what is the topic of your conference, because you wouldn't be able to know who you're going to invite unless you knew what the conference is going to be about, right? So, I mean, there's a place that you would start at the top. What is the topic? Now I know the topic. I can invite the right people. Once I get the right people, I can maybe think about where I'm good. No, not even that. Yeah. How many chairs, then where they're going to sit, and then who's going to do the advertisement. Last thing, it would be the day before, the snacks. Because I mean, worst come to worst, you could just call for pizzas or something, right? You know, I mean, the snacks will happen. You know what I mean? Absolutely. And it's not going to be that big of a trouble. I'm running out of time, so I'm going to try and rush through that. So I'm not even going to go on that. So yeah, defining the goals. I'm just going to leave that as saying you need to know what it's going to look like at the end. And it would be better if you wrote it down somewhere, right? If you wrote it down, this is what my goal is. Okay, what do we got here? Decomposition task. Got a policeman and a lady at a jewelry store. A crime's been committed. Solving the crime, very complex. Police officer needs to know the answer to a series of smaller problems. Look at the crime sign. What problems do you need to do? What crime has been committed? When was the crime committed? I'm cheating because the answers are down there. You see that? Can you cheat there too? Being a detective, it would be, this is a police detective, right? That's what we do too. Analysis, business analysis, program analysis. You might find yourself as a program analyst, where you have to ask questions like that, not about crimes, but for us, unless you're writing a computer system for the police force, you're not going to be asking these questions, but you could be asking questions like, you know, What is the data inputs that you need? What are the outputs you need? What do your reports need to look like? You know, where do you get your data from? These are kind of things. They're kind of questions like this, but would be related to whatever problem you're trying to solve. The policeman is thinking this way all the time. You know, okay, so where can I pick up my evidence to help me solve this problem? And these things are all evidence. Was there any witness? Yeah, if I had witness, I'd probably talk to him. All right, so here we have those things put together as if any of you want to ever be a policeman. I don't know, or detective. What crime was, you know, was somebody stole something? When, where? Do we have any evidence? Do you guys ever watch those police shows? I like to watch them. And I mean, they just do this type of stuff, right? In a way, detectives are kind of like the scientists I was talking about, right? They form a hypothesis. I think so-and-so did it. Now I have to go and prove that so-and-so didn't do it. And if I can't, and that's what they do, right? Actually, I watch a lot of those murder shows. I don't know why. It's terrible, right? But you know, so the first thing they do is so-and-so died. Well, first thing we do is go and talk to their husband or wife. And then we find out if they have an insurance policy, right? If we do, well, then we really talk to their husband or wife. But, you know, we talk to their husband and wife. And what are we going to talk to them about? We want to prove that that husband didn't do it or that wife didn't do it. You know, where were you at such and such a night? Oh, you were at such and such place. Well, you couldn't have done it. Thank God. Now we'll have to go and talk to somebody else. Right. So that's kind of like the scientist in the hypothesis. We try and prove that it wasn't that person. And when we can prove that it's not that person, then we go and look at something else. If we can't prove that it wasn't that person, well, guess what? That person is going to jail and they're going to stand in front of a judge. And then the judge is going to try and prove that it wasn't that. Or you with me? So that's kind of scientific, isn't it? Detective. It's so yeah, these things sort of relate. All right, so what are we going to do here? We're going to make a sandwich. We're going to decompose the sandwich. Well, yeah, I mean, you know, because we got different parts of the sandwich, right? We don't just throw it all together. We have a step by step, and there's different parts of the sandwich. So what do you do? So before we make the sandwich, we want to know what kind of bread. This is what the people at Subway ask you, isn't it? You guys ever go to Subway? All right, so when you finish this, you can get a job at Subway. All right. Everybody ready to take a job at Subway? So what do? What type of bread do you want? Do you want butter? Or do you want mayonnaise? Or do you want olive oil? Do they offer you that? That's just butter or mayonnaise, right? What do you want on it? Blah, blah, blah. And is it toasted? I think we're running out of time on this. I know that because we've got 1 minute left, and then the recording is going to stop. I'm going to stop, and you guys can leave for a minute if you want. And then we'll come back and do lecture 6. Is that all right? And I'll put the Zoom on. So I hope you'll come back. I hope I didn't bore you so much that you didn't come back. If you're really bored and tired, then you probably do need to stand up and go for a walk.